Okay, today we're looking at our first chapter, which is dealing with a review of all things general chemistry. Now, while it is a review, we're going to touch on how it's going to affect things throughout, and we do hit on everything in this chapter multiple times. So by the end of Organic 1, you're going to be very good at everything that we cover in this chapter because we're going to be using it again and again and again. All right, now organic chemistry gets its name from the fact that at one time, anything that was considered organic was something that at least was once living. Now, back in the 1800s, they were talking about something called a vital force, as in there was something in a molecule that had to be created in something that was living, and if it was from a mineral, something that was never living, it doesn't have that vital force. And it wasn't until about 1828 when this guy here in this picture here actually made an organic molecule for something that was known to be inorganic. He made urea from ammonium cyanate. And since then, we've actually changed our definition. Organic chemistry is just something that contains a carbon. Now, why carbon? Why is it so darn important? Well, it turns out carbon, being where it is in the periodic table with a low electronegativity and right in the middle, has 4 electrons. It can actually make a decent bond with just about everything. And more importantly, it shares them. It almost is willing to make a covalent bond with everything. Because of that, it increases a lot of versatility, and there's a lot of changes or characteristics that are unique to carbon and the bonds it makes. All right, before we get into actual true organic chemistry, though, we're going to do our true review. All right, so structure atom is no different here than it has been since intro. There's protons, neutrons, and electrons. You can get the atomic number. Ironically, we will not use the atomic number all that much in this class because we're dealing most with carbon. Carbon has 6. We could use a very simplified periodic table just because of how few atoms we actually end up using. However, isotopes, which are the exact same thing chemically speaking, the only thing different is their actual masses, will actually have a critical benefit. Later in the semester, we're going to see something called a mass spectrometer, which actually measures the intensity of peaks that are related to the mass. It's a mass to charge ratio. And when you see something that has carbon in it, you always see a big, huge peak and a little tiny one, just one little unit above that. And that's mainly because 99% of the time you have carbon 12, and about 1% of the time you have carbon 13. And those peak differences are corresponding to that 99 to 1. Get a really, really, really good mass spectrometer, you might see that carbon 14, but its amount is so small, it's very unlikely you would see carbon 14 even in some really good mass spectrometers. Now, where that's going to come in handy is everything has isotope ratios that are differences. And on that mass spectrometer, we can typically tell the difference between, say, a carbon and an oxygen based on just an isotopic breakdown or what the size of those related peaks are. All right, but that's later in the semester. Right now, we're just talking about the fact that there are isotopes out there. And right now, we're going to point out that they chemically behave very similar. So carbon 12, 13, and 14 are used in our bodies all the exact same way with no differences whatsoever on how they're chemically responding. All right, when the electrons are distributed in a cell, or in an atom, they are distributed by their proximity to the nucleus. And we had our orbitals that we talked about in general chemistry, and that's what we're talking about here. The atomic orbitals move up in different levels, getting away from the nucleus, and we talked about the energy level and the shape level and even the orientation levels back in general chemistry. And we're talking about that same stuff here because it does factor into how they chemically behave, because their shapes are going to help us understand why certain bonds behave the way they do, and their levels are going to tell us why certain bonds are weaker than others. So we're revisiting some of this stuff. We are going to simplify it a lot because most of the time we're talking about S and P orbitals only. D and Fs don't really enter into organic chemistry that often. All right, matter of fact, even when we're distributing our atomic orbitals, we will use electronic configuration, so we will need to talk about the D's and the F orbitals even, but we really don't get that high, because even if we're looking at carbon, the central being of organic chemistry, its electron configuration, we never can get above the second shell. But we are reviewing this stuff because electron configurations are darn important for some of our later chemistry, some of the stuff we look at in later parts of organic. Now, I am going to point out this little list I have here that's missing something. Because while the next set of data is our 4s, the 4p, the 4d, and the 4f, I do want to point out that if you don't remember this, 4s actually fills and has lower energy than that 3d orbital. Remember how they didn't fill in order? Well, that was related to the different names of guys who figured out different aspects of our electron configuration, how they go. Aufbau principle was the one talking about how the order of which they fill. He was the one that explained that why the 4s orbital fills before the 3d orbital, because it just turns out the 4s is lower in energy. Now, Pauli was the guy that actually came up with the concept that you can't put more than 2 electrons in an orbital. So we said if you have a box representing one of the orbitals, we put 2 electrons in, and the next electron goes into the next highest box, whatever that is. Hund's rule was talking about when we have degenerate orbitals. Remember how the p block of orbitals, there were 3 of them? So if this is the second shell with the p orbitals, there were 3 degenerate orbitals. And we will put an electron in each one of those before we start pairing any one of them. All right, next thing we're looking at is just some refresher terminology. Turns out most of our metals end up losing electrons when they form ionic bonds. They actually, most of them, it's safe to say, they like to lose electrons. When they do that, they become cations. And on the right side, the nonmetals typically accept electrons and become anions. And that's going to introduce covalent bonds to a degree, because hydrogen, which actually does make hydrogen covalent bonds, also can be cations and anions. So hydrogen itself we have introduced in general chemistry, where 2 hydrogens bump into each other and make a covalent bond. But it turns out hydrogen could have just totally given up the electron and made a cation. Hydrogen might just accept an electron and make an anion. Even though it's over there with the metals on the periodic table, it actually can behave like a nonmetal and lose the electrons as well, or gain the electrons as well. All right, but the sharing of the electron is going to factor in as well. All right, so back to our anions and cations. They actually typically form ionic bonds when they get together, and ionic bonds are various different crystals. So we got sodium chloride here representing it, and that is just an attraction. There's plenty of ways to overcome it, but if it's related just heat, so trying to melt sodium chloride, it require a lot of energy, because that shows how strongly they're attracted to one another. All right. Next thing we're looking at here is the covalent bonds. Now, we just showed on that previous thing dealing with hydrogen, that very first one where the 2 hydrogens actually overlap and form a bond, and we typically end up drawing that something more like so. And even the fluorine, we typically see it drawn more like this, where the electrons that are overlapping between the 2 get turned into a line. And that line represents the sharing or the covalent bond. And if it's a heteroatom like HCl, we get something very similar as well. All right, but the reason we're showing this differently is because we're showing covalent bonds and how they can become polar, which is when the electrons are not being shared evenly. So our 2 up here that are dealing with heteroatoms, or homeoatoms, where they're both the exact same, those electrons would be shared very evenly, and we would have more of a nonpolar bond. But HCl, because of the electronegativity difference, the chlorine would get the electrons more, and we'd have a polar bond. We typically get polar bonds anytime the atoms are not the exact same. All right, all of these would actually create polar bonds because the hydrogen is going to give up its electrons more often than the other atom. But it does form different statuses. So, and we are going to revisit our Lewis structure so we can see how we could come up with these here in just a bit. All right, but that unequal sharing is dealing with the electronegativity and the fact that things like fluorine don't like to share evenly with anything else other than another fluorine. If fluorine's making a bond with something like hydrogen, with that electronegativity difference of over almost 2, the electrons are spending almost all their time with fluorine and none of their time with hydrogen. Actually, fluorine-hydrogen bond is so polar, it almost behaves ionic. All right, so we actually see that as a benefit in organic chemistry. When we see that unequal sharing, that polarity of a bond, that actually will create an avenue for some reactions. Anytime you have that unequal sharing of electrons, you have a place where you can start a reaction. That's actually a good thing for us in our later chemistry, later parts of this class. All right, and various different things to give us various different polarity or dipole moments based on the bonds. These numbers aren't really that critical to know. We just need to know the trends on why they go up and down, and you can base that on where the two atoms are and those electronegativity differences. You can just basically look at the difference, and that relates to that dipole moment almost directly. All right, we will actually see this a lot in our textbook. It's on electrostatic potential maps. Now, all that is, it's actually showing like the outermost area where you'd find the electrons 90% of the time for the majority of the entire atom, or the entire molecule, that is. So these are molecules, and that's the electron cloud for that entire molecule, and we're color coding it based on where the electrons are most likely to be found. And if you're signed up for the lab later on in the semester, we'll get to use a program where you can generate electrostatic potentials for almost any atom or any molecule you can think of. I say almost. The bigger the atom it is, the longer it takes to calculate an electrostatic potential map. All right, on to something else we're going to be reviewing here, formal charges. Now, we used these back in general chemistry to tell us whether or not we actually came up with a successful Lewis structure. And if we were to do something like carbon with 4 hydrogens on it, we could get its formal charge just by looking at the valence electrons of the carbon, which would be 4, minus half of the electrons that are bonding. There's 2, 4, 6, 8, so that would be 4. And then the unshared electrons, there are no pairs of electrons in that. So that particular carbon has a formal charge of 0. Now, saying that is interesting, and figuring it out is interesting, but we're going to see that a lot of the times we draw our carbon atoms the exact same way. What I mean by that, methane and ethane, both of these have carbons that have 1, 2, 3, 4 bonds and no lone pairs. 1, 2, 3, 4 bonds, no lone pairs. 1, 2, 3, 4 bonds, no lone pairs. All of these, the formal charge is 0 for that particular carbon. Matter of fact, all those hydrogens are 0. And once you actually start seeing that that is a good way to draw carbon, and that's a very common way to draw carbon, we can say that will pop up anytime. Anytime you see carbon with 4 bonds, doesn't matter how we make those 4 bonds, you're going to have a formal charge of 0. But let's look at some other deviations. Sometimes carbon doesn't have 4 bonds. There are methyl cations where the electrons are just not there anymore. There are methyl anions where the lone pair there's a pair of electrons there, and there's methyl radicals. These all have different formal charges, but we can figure that out because 4 valence electrons minus, that would be 3, 6 divided by 2, and no lone pairs. That particular carbon has a formal charge of positive 1. Over here we have 4 and 3 and 2 for those 2 pairs. Sorry, that would be not. Excuse me. 4 minus 3 minus 2, that would have a formal charge of negative 1. And then the last one, we have 4 and 3 and 1 unshared electron. That one has a formal charge of 0. Now, I'm writing out how I figured this out, but we're going to get in a good habit of realizing anytime you see a carbon with 3 bonds and a positive, it's got a positive 1 formal charge. 3 bonds, a lone pair, and a negative, it's a negative 1 formal charge, and that radical is a 0. I want you to know how to solve the formal charges, but you're going to see the same ones a lot. Even nitrogen, there's really only 3 ways we ever really see this. So if I know that this nitrogen has a formal charge of 5 minus 1, 2, 3, 4, 5, then I know these two both have a formal charge of 0. And if I figure this out, 5 minus 1, 2, 3, 4, that has a formal charge of positive 1. 5 minus 1, 2, 3, 4, 5, 6. That one has a formal charge of negative 1. And anytime you see nitrogen with 4 bonds and a positive, it's going to be a positive 1 formal charge. And we can do the same thing with oxygen. Formal charges up here are 0. 6 minus 1, 2, 3, 4, 5, 6. 6 minus 1, 2, 3, 4, 5, 6. Down here it'd be 6 minus 1, 2, 3, 4, 5. Positive 1. And if you look it up, you'll figure out that that formal charge is negative 1. Okay, now once we know that, we can actually figure it out a lot, but we're going to see the atoms we see most of the time in organic chemistry are only drawn a few certain ways. Hydrogen, for instance, we're going to see it as a positive, a negative, or a radical. Halogens, all of our halogens, negative ions or radicals. You actually can figure out the formal charges almost just by looking at the structure, because once you know what a formal charge of a particular atom is, it's that same way every single time we draw it that way. Now, something that does come in handy for organic chemistry, especially in our Lewis structures, is the fact that almost everything behaves a lot like these guys, in the sense that there are going to be 4 groups bonded to each atom. Hydrogen only going to have 1 bond or a pair of electrons, but all the others, carbon likes to make 4 bonds, nitrogen likes to make 3 bonds and 1 pair of electrons, oxygen likes to make 2 bonds and 2 pairs of electrons, halogens like to make 1 bond and have 3 pairs of lone electrons. Well, this always adds up to 4. If we double that, it's 8. If you remember back in general chemistry and intro, we talked about the octet rule, and then we threw it out and said it doesn't really apply. Well, here in organic, it does. Most of the time, the octet rule is being followed. And the times it's not, on almost all of our chapters that deal with oxygen, we'll have something similar about sulfur, which is right below it on the periodic table. Now, I say similar in the sense that almost everything you can do with an oxygen-containing carbon compound, if you replace the oxygen with sulfur, the same reactions apply. But since sulfur can break the octet rule, there are always a few more reactions for this. There are just a few changes based on the fact that sulfur doesn't have to follow the octet rule. But since all the others do, the octet rule is something that gets referred to a lot in organic chemistry. Okay, let's back up on our Lewis structures, because we were drawing these pictures before with the pairs of electrons as individual dots. Technically, we would have said that was wrong back in general chemistry, because we knew back then Lewis structures should have them drawn out. Now, we do want to actually make sure we remember how to do Lewis structures, because we are going to use them a lot. But we will find our molecules are awfully big, and Lewis structures will not be used always. All right, so let's refresh how we do our Lewis structures. We're going to do this for NO3 minus. I like how that minus is way down below. It should be up here, but it's okay. All right, so remember, first thing we're going to get is our valence electrons for the entire molecule. Nitrogen has 5 valence electrons. Each oxygen has 6. That negative adds 1 more. So this atom has, or this molecule has 24 valence electrons. Number 2, we're going to arrange them in space. In this case, I'm going to put the nitrogen surrounded by the oxygens. And I'm going to remember that since this is a polyatomic ion, it's very likely that whatever's not oxygen is surrounded by oxygen. because that's typically how we see our polyatomic ions. Our third step, we're going to distribute the remaining electrons. So I got 2, 4, 6, and I'm going to put them on the outside atoms first. 8, 10, 12, 14, 16, 18, 20, 22, 24. And then step 4 is where we actually rearrange them to make everything follow the formal charge. That's how we did it in general chemistry. Intro, we actually follow the octet rule. Well, this being nitrogen and oxygens, we really just need to follow the octet rule. So that nitrogen right there is not happy because it only has 6 electrons around it. So I'm just going to grab 2 off one of those oxygens, and I'm going to actually pull them off the last one I just drew and make a double bond there. Now this one will resonate. That double bond can move between all those 3 different locations, and that lone pair moves around with it. But that would be our Lewis structure for NO3. Okay, now the biggest reason we don't see the Lewis structure as often as other structures is simply because our atoms are getting, our molecules themselves are getting much, much bigger. So one of the first things we'll start to see is you sometimes see where the electrons are not drawn. That bromine and that chlorine should have electrons drawn on them, but they're just left off because once we get to organic, we probably know that they're supposed to be there. So we start abbreviating them just to save time. And we even do weird things like this, where this carbon here has another carbon off of it. And rather than having a carbon with those 3 bonds drawn off of it, they've just condensed those carbons. Well, since we're doing that here, what we're seeing onto the right side here is what we call more of a condensed structure, where we're actually going to condense all these carbons down to CHs, and then a number to represent how many hydrogens there are. And then we're just going to basically turn this Lewis structure into a straight line text. Sometimes we'll deviate it out to show where these bromines pop off. You can see how that has that bromine there. That is saying it's attached to the previous carbon, even this one attached to the previous carbon. But over here, they just made it into a 2-line thing and put the bromines down below. But we're going to see these condensed structures a lot simply because they're easier to write. That's a single line of text with just subscripts. You will see Lewis structures without the lone pairs. We're going to call them Kekulé structures a lot as well. Now, another weird thing that pops up with Kekulé structures, you sometimes don't draw the hydrogens at all, and sometimes the carbons aren't labeled. What I mean by that, this thing right here, which has 1, 2, 3, 4, 5, 6 carbons in it, will sometimes end up looking just like this. These intersections are representing the carbon, 1, 2, 3, 4, 5, 6. And the hydrogens aren't drawn at all. They're just assumed to be there if they're at the end of the line. So since that's representing a carbon, if it's only bonded to one other thing, there must be 3 hydrogens on it. They're just intentionally left off. Now to make this fully this one, on the second position, I need to actually draw the bromine. And on that second, third, fourth, fifth position, third, fourth, fifth position, I need to draw that chlorine. And this is also a Kekulé structure. It's just a lot more simplified. And if you think about it, at least drawing-wise, wouldn't that be a lot quicker to draw than this or even this? Yeah. Yep. They all represent the same exact molecule. But Kekulé structures are a lot more common. Think of them as Lewis structures where the lone pairs are not necessarily drawn. All right, and we see those a lot. These Kekulé structures are going to pop up and out throughout most of the book. Matter of fact, seeing things like this are going to get less and less common. You're going to see carbons drawn out very rarely. This would be a lot more commonly drawn structure in your textbook. And if we wanted to focus on maybe that bond right there, you might see it drawn where just that bond is expanded. And what I mean by that, they might actually just draw out that CH3 as more of a Lewis structure and leave all the rest condensed like they're drawing it. So we will see Kekulé structures that are expanded where the book feels it needs to be to explain it. And you might even see lone pairs added in that particular case if the explanation needs those lone pairs to show what's going on. But we see quite a few different ways of drawing the structures. Condensed structures are far more common, especially early on in the textbook. All right, so back to our review. We were introducing the atomic orbitals in the sense of electron configurations, but now we're going to talk about those shapes and how they apply. So on this page, I have the s orbitals, and those were the simplest ones. They just basically look like balls or spheres. And a 1s orbital is smaller than a 2s orbital. And that's really all that's really talking about. And it's talking about what a node is. And we're going to expand on that node thing because it's a little bit more obvious than something like a p orbital. Now, if you remember, the p orbital was created by putting a fold into an s orbital. Another way of saying a fold is we've put a nodal plane in there. We've got the upper half of the orbital and the lower half of the orbital in totally different phases. That's what that positive and negative represent. That's created a nodal plane. There's a plane right through the atom where you're not expecting to find a moving electron. And this is just a different way of drawing it. It says computer generated. These were probably all computer generated, but based on your percentage of where you want to expect to find the electron, you'll get different shapes. Your book ends up using both far more often. All right. Then we also have our different orientations. The p orbital, the p block, for instance, always had 3 orbitals whenever you drew out a full block. This is representing those orientations, those 3 different orientations. All right. Now, we're going to see anytime you create a bond or a covalent bond, we're going to create an overlap. And the basic overlap, anytime we actually see a bond, we know that's a sigma bond. Now, all a sigma bond is a mathematical representation of that overlap. That overlap, turns out, is lower in energy than the actual atoms individually. So it's beneficial to the molecule to let those overlap because it makes a better orbital. That sigma orbital is lower in energy. Now, mathematically, the equation kind of looks something like this. If we have our mathematical equations that represent an s orbital and we mathematically overlap them, and we get them to a certain degree where they're close enough, they create this new orbital that has constructive contributions and makes a more stable orbital. Now, the s orbitals could be added out of phase. That's what's shown in here in B, where we just invert one of them, and that creates a nodal plane. Now, this actually is the representation showing us our sigma bonds and the sigma stars, the antibonding orbitals. And we're seeing what they kind of look like. So we have that overlap where the atoms want to bond and the orbital is lower in energy than the 2 s orbitals that created it. And then we have an equally bad orbital where they're out of phase to one another. Now, mathematically, both these exist, but if we're dealing with something like hydrogen, which each hydrogen just brings 1 electron to the molecule, those both go in the lower, more stable bonding orbital. So HH bonds. But if I were to change these to helium, we would be adding a second electron because helium has 2 electrons, and those other 2 electrons would have to go up here into this antibonding orbital. As much as these 2 would want to make helium-helium bond, these 2 really, really don't. So helium and helium, we get no bond. They will not bond to each other because they have too many electrons in that antibonding orbital. All right. Pi bonds are formed when p orbitals overlap parallel to one another. And that's what they're kind of showing here. They're both straight up and down on the paper, and when they overlap, they stay parallel to one another. That overlap happens above and below the line between the 2 orbitals. So if the sigma bond's right here in the middle, the pi orbitals are above and below. And along with the possibility of creating this pi orbital, there's also the chance of making an antibonding orbital, which is just where the phases are out of alignment. So we get 2 nodal planes. Get the nodal plane that goes through the middle, where the nodal plane was for the individual p orbitals, and then we get one going right down the middle of the atom itself. All right. Now, biggest reason we're bringing this up is the p orbital overlaps are going to help us explain what's going on with pi bonds. Turns out it kind of helps us understand what's going on with electronegative atoms. So it turns out our more electronegative atoms, like oxygen compared to carbon, the p orbitals themselves are slightly lower in energy than carbon's p orbitals. When that overlap happens, we create an imbalanced pi orbital, where the electron cloud of that pi bond favors the oxygen side. And simply because of that, the electrons spend a little bit more time closer to the oxygen, or the more electronegative atom. All right. Next thing we're looking at is how our atoms themselves are bonded in much more complex molecules. So we're going to start with methane. Methane, actually, if I were to draw it out as a Lewis structure, we would end up with something that looks like so, which on paper just looks like a cross or a T. And it would probably be related to geometry class as having 90-degree bond angles. But the actual methane is a three-dimensional molecule, and all these pictures down below are trying to stress the three-dimensional nature of it. So on that first one, we basically have almost a Lewis structure, but we have wedges and dashes to indicate coming out of the paper, going into the paper. Now, there are other ways to do this, but that's the best way to do it on paper, is with the wedges and dashes. The next two are just different ways of trying to draw the atoms as balls and sticks. This one, just the balls are bigger and there's no stick anymore. But that ball and stick, we do a little bit of shading and size differences to create that 3D effect. And the program I talked about we're going to use in lab, you'll get the chance to make these. And we will have some of this pop up in lecture with that same software to show shapes of molecules that are that have some asymmetry to them, that have like a stereochemistry. All right, but when we actually make that bond, we need to overlap different types of orbitals. So that's what we're actually relating it to, the hybrid, the shape of the molecule to the hybridization of the orbitals. Now, something like methane, if I back up here, all of these show that that carbon itself is bonded to 4 different things. Every single way we draw it shows the 4 different things it's bonded to. That means we need to overlap 4 orbitals. So we're going to take our 4 lowest and make 4 sp3 hybrid orbitals. And we're not doing anything different than we did in general chemistry. It's just a straight overlap of those orbitals to come up with what we need for hybridization. And it doesn't matter how we view it. We're going to actually overlap those 4 orbitals, even as boxes or letters or the actual shapes themselves. And our hybridization almost always creates the same thing. We get a lobe that's bigger on one side and smaller on the other. And they orientate themselves as far away from each other as possible. So they form that tetrahedral shape that we expect carbon to go through when it has 4 groups on it. We see that even if we have a more complex molecule. So something like ethane that has 2 different carbons, since each of those carbons has 4 bonds coming off of it, we'd still expect each carbon to have sp3. Now, the neat thing is, because of how this overlap is, this bond is going to be able to rotate. So we will see that this has different ways of orientating itself. Right now we have it drawn where these 2 are down and this one's down, but we could rotate this and we could end up with something where it almost looks like it's a mirror from the left to right. So that middle bond does actually rotate. There's nothing stopping it. Now, if I go and look at what the p orbitals do, I'll see that the p orbitals can do the exact same type of thing and make a sigma bonds. Just have to have the p orbitals or the sp orbitals overlap in phase with each other. What I mean by that, they need to overlap where they overlap directly between the 2. If the overlap is directly between the 2, you get the sigma. And if you do those out of phase, you get that sigma star, always. All right, ethene Very similar to ethane, but it has 2 fewer hydrogens. Lewis structure shows it has a double bond. Well, we could also look at this as having this carbon has bonded to 3 different things. So I need to just overlap 3 orbitals. So I'm going to make 3 sp2 orbitals and have an empty p orbital. All right, that creates something kind of interesting in this case. Those 3 sp2 orbitals are going to form a trigonal planar shape. They're going to be on the same plane, 120 degrees apart from each other, and the remaining p orbital stays perpendicular to both those. All right, that actually helps us on predicting some cool things about the chemical shape. Even though most sigma bonds can freely rotate, this one can't. Because while this doesn't show any limitations to it, when we throw the pi bond in there, the pi bond can only exist if these two are perfectly parallel to each other. So that's going to stop this thing from rotating. It can't rotate because if it were to rotate, it would break that bond. So suddenly, without that, this is a very rigid structure. And very cool, if we were to look at our actual stick drawings, we can actually safely say that these hydrogens and those 2 carbons, can't even see the color I put them, must be on the same plane. They can't rotate anymore. It's going to be a perfectly flat molecule. Now, something else we can see on the electrostatic potential map. You notice that red buildup there? Well, that color change is going to help us out when we start to see chemical reactions. The previous one with ethane, we're going to find there's very few things we can do to ethane that has nothing but carbons and hydrogens and nothing but single bonds. There's only a few chemical reactions that will work. But that double bond with that higher intensity of electrons right there, this is going to be a little bit easier to do reactions with. There's going to be a lot more we can do with an alkene, something with a double bond. And if I make that a triple bond, it's even more reactive. But nice thing to see, 2 bonding groups. I only need to combine 2 orbitals. So I'd have 2 sp hybrid orbitals, and the remaining 2 would be p orbitals. These 2, the sps, would actually get about 180 degrees away from each other. And it would end up looking something like this. 180 degrees to each other, and the p orbitals are actually 90 degrees to that, and they're 90 degrees to each other. So when it, as in the acetylene, makes a big strong bond, it has a very big density, very difficult to rotate this bond. You wouldn't see much though, because this one can rotate and this one could rotate, but it's a nice linear molecule, huge amount of red in the middle, so a lot of reactions can happen with that triple bond. All right, the methyl cation and the methyl radical we introduced way back a few slides ago. Methyl cation was where it had the 3 hydrogens and just a charge. The radical had the 3 carbon-hydrogen bonds and a single lone pair. Turns out their shape is exactly the same. Now, this upper shape makes sense because this is just 3 groups. So we would say sp2 hybridized and trigonal planar. But when I would actually have asked you about the methyl radical, you probably wouldn't have known what to do with that single lone electron. Because we covered in general chemistry what to do if there's no electrons. You just don't count them. And if there are pairs, you treat it as a pair. So it was always pairs of electrons. But this is a radical, has just 1 electron. Turns out when you have just 1 electron in an electron cloud, it doesn't count towards hybridization. It will never go into a hybrid orbital. It will stay in something like a p orbital. So when I look at the methyl radical, I actually just count those 3 groups. So this is also sp2, and it's also trigonal planar in its shape. And that lone electron's in a p orbital, which does affect the electron potential map because that 1 electron's located right along that in that p orbital, go up and down through the middle of the molecule, but it's not actually affecting the shape of the molecule. All right, when we introduced those 2, we also introduced the methyl anion. The methyl anion has 2 electrons on it. It's a CH3 with a lone pair. All right, because it's a lone pair, it will fill up a full orbital, and this has then 1, 2, 3, 4 things. so it needs sp3 hybridization, and it is trigonal pyramidal. All right, our next thing we're looking at is some of our heteroatoms and seeing how we can figure out their hybridization. Ammonia really isn't any different than a carbon in how we figure this out, because we really do just count our bonds. 1, 2, 3 things it's bonded to, and a pair. We need to overlap 4 things. We're going to overlap all 4 and make 3 or 4 sp3 orbitals. No, it doesn't say that, but these are going to be sp3 hybridized. And same thing, for the most part, applies even if I made NH4. NH4 will be a positive, but it still has 1, 2, 3, 4. That's still sp3 hybridization necessary. Water, 1, 2, 3, 4 things, needs sp3 hybridization. And even our halides do the same type of thing. Our halides, we would just have 1 bond, but our book points out that that would prefer, because of these lone pairs, 1, 2, 3 pairs of electrons and 1 bond. That's 4 things, so they're going to go with the 4 sp3 hybridized orbitals. It helps explain how the electron density is, so we're sticking with that. All right. Along with that sp3 on those heteroatoms, it turns out we can start predicting things like bond strength and bond length based on what atoms are being bonded. Now, where that plays in, we have to look for some similarities. So what we're going to start out with is looking at just our halogens bonding to hydrogen. Biggest reason we're doing that is because we can rank the size of the bonds, or the length of the bonds, to the size of our atoms. And since HF is since fluorine's the smallest atom, this is going to probably be the shortest bond. And it is. And this one is the longest. And it really is just related to that size, because the only thing that's really different here is the actual size of the nucleus. This is still an sp3 hybrid orbital, and this is an sp3 hybrid orbital. Both of them are made by the overlap of s and p orbitals. It's just that these are a much smaller orbital. They're only in the 2s. Yet this is an overlap with a bigger principal quantum number, which is why it's a bigger orbital. So it's going to be shorter and longer. Now, strength we can actually see is directly related to length. And what I mean by strength, see this overlap here, they're all sigmas. But the sigma here with HF is much closer to both nuclei. So it actually makes a stronger bond. And when that overlap is very far from the 2 nuclei, it's a weaker bond. And we see that's always the case. A shorter bond is always stronger than a longer bond. And we can see some interesting numbers from that. So I got some bond lengths that were actually calculated in angstroms, or figured out in angstroms, and we're relating that to the bond strength. We're going to see something interesting. Here early on in the chapter, we actually almost always see both units used, kilojoules and kilocalories. And that's mainly because in general chemistry, we focus mostly on kilojoules. Now, we're going to get away from that a lot as we get further in chapter and start using, or in the book, and start using kilocalories a lot more. And that's really because this relates to food calories. Helps us relate it to things a little bit easier in many cases. All right. So our summary of our hybridization. To figure out your hybridization, you really are just counting the things, the groups that a central atom's bonded to, and combining the orbitals you need to get that. Once you have the hybridization and once you have the Lewis structures, you'd have the hybridization, your bond angles, and the shape. So Lewis structure gives you all of these. And everything we did in general chemistry works here. It's just in general chemistry, you also talked about sp3d and sp3d2, and we really won't see that here. And if we look at just a straight Lewis structure, we can always tell how many bonds are sigma and how many bonds are pi's, simply because any single bond or a single line is a sigma bond, Any double bonds, one of them is a sigma and one of them is a pi. And any triple bond, one's a sigma and the other two are pi's. It always happens that way. You never get a pi bond first. Now, something like this happens a lot. We will actually see on your test structures drawn out and little arrows underneath atoms like this, or maybe a atom that's in bold type, and you're just asked to identify the hybridization. You don't need to get terribly crazy on this. You really can. If I want to ask something like nitrogen here, to figure out your hybridization, just count how many things it's bonded to and they lone pairs. That nitrogen is bonded to one carbon, one nitrogen, so two things, and one lone pair. So it's got 3 bonding centers off of it, so we would need to combine 3 bonds. Therefore, we need sp2 hybridization. Okay, other things about bond lengths. Turns out a double bond and triple bond are shorter than single bonds. Now, that really happens to do with the fact that even though we're shoving more electrons in there, we're actually increasing the charges. The negative charge is pulling in the 2 positive nuclei even more. So a triple bond is the shortest, and therefore it is also the strongest. And we can see some actual numbers to that too. Oh, I don't have that on the next page. But the triple bond is much, much stronger than a double or a single. All right. Now, another characteristic we talk about when we talk about these bonds is we talk about their S character. Now, S character simply means, looking at the hybridization that would go in, an sp hybridized bond has more S in it than an sp2 or an sp3 because of how many orbitals you've overlapped. In an sp, you overlap a single s orbital and one p orbital, so 50% of it's still an s orbital. But sp2, it's one s and two p's, so it's only 33% s. sp3 is only 25% s. So it turns out more S character gives you a stronger and shorter bond. And that really applies on almost anything we deal with. Anytime you see something with more S character, you're going to have a shorter and stronger bond. So hydrogen, which only has S, an sp3s bond would have more S character, so it would be expected to be shorter and stronger than a bond between 2 carbons, which is just an sp3 and an sp3. So while it doesn't always work, and there are a few exceptions, we hear more S character throughout the book. And that is really talking about the hybridization of the atoms involved in the bond you're making. Turns out the S character also helps you predict the bond angles. The more S character has bigger bonds. All right, and here's a summary of all that stuff with some bond strengths. Here's our double, single, and triple bond, and we get the bond strength of 90 to 170 to 230. So it's not triple it, and this is not double it, but we are seeing a steady increase in the strength of the bonds as we add those pi's in there. Now, that's that summary. Speaking of that double bond and that difference, though, if we were to look at the strength of a sigma bond and the pi bond in the double bond, we are going to always see that the sigma bond is much stronger than a pi bond. That probably makes a little bit more sense if we think about it, what it means. If you think about the overlap between the 2 carbons, the sigma bond always happens directly between the 2, where the pi is an above and below that, and it's split among the 2. So it does make sense that that sigma bond would have to be stronger. All right, next thing we're looking at is dipole moments of the molecule. Now, dipole moments are going to be a result of the molecular dipole of every bond in there. So we have, in both these cases, we actually have slightly polar bonds. Carbon and oxygen, oxygen's more electronegative, so the electrons go out, which is why in this electron potential map, we see the red on the outside. Even on carbon tetrachloride, carbon has electronegativity of around 2.5, chlorine's closer to 3, so the chlorine's more electronegative, so the electrons are going out away from it. But both these molecules end up with no dipole moment. They're both nonpolar molecules. And it's mainly because even though they're made out of polar bonds, the polar bonds are symmetrical. On the carbon dioxide, they're directly across from each other. They cancel each other out. Now, we do see something beneficial that electronegative difference in this that this potential map is showing us is going to help us understand why certain molecules react the way they do. But dipole moments of molecules relate to their physical properties, like boiling points and freezing points. And both these are affected by mostly just dispersion forces because they're nonpolar molecules. But as soon as I add some asymmetry, change one of those atoms on my tetrahedral arranged carbon to something different, I'm going to have a polarity simply because of that. The the dipole moments of the individual bonds will not cancel out if I have a single heteroatom that's not balanced out. If I have electron pairs, there's no way it's going to balance out. So as soon as I get that asymmetrical layout, I'm going to have a polar molecule which has a dipole moment. And these will have physical properties affected by that. Boiling points and freezing points will go up with the dipole moment. All right, last little thing I want to do, intra versus intermolecular forces. Now, reason we need to revisit this right now, and we're actually going to talk on this topic in almost every chapter, is because we did this weird thing back in the past of, remember that like dissolves like statement? Like dissolves like. And basically what that meant was things like water dissolved or mixed with things like ethanol because of those similar intermolecular forces. Water can make hydrogen bonds. Ethanol can make hydrogen bonds. And since they can both make hydrogen bonds, they can actually mix. And if I wanted to go over here with something that doesn't mix with water, I might actually go with just propane. Propane can do nothing but London dispersion forces or dispersion forces. Because they're totally different, like dissolve like says these two don't mix. All right, like dissolves like still mostly works, but we're going to start dealing with some weird gray areas where hydrogen bond molecules, London dispersion molecules, and dipole-dipole interaction molecules start to overlap. What I mean by the overlap, let's take this propane or this ethanol and just add a couple more carbons to it. So it's the same exact molecule with one more or two more carbons. We're going to call those butanol. That's what we're going to see the name of it is. Now, something neat about butanol, that OH, this does do hydrogen bonds with itself. And because it can do hydrogen bonds with itself, it has increased boiling point, increased freezing point over something without hydrogen bonds. It's going to be a liquid at room temperature. All right, but hydrogen bonds that like dissolves like would imply that this should dissolve or mix with water. And it does, kind of. But this part of the molecule is a little bit too long, and it favors dispersion. And just because that chain's getting longer and longer, the solubility in water is much, much, much lower. I think it's only like 1 or 2 milliliters of butanol is soluble into a liter or 100 milliliters of water. It's pretty low. But we're going to see this overlap some. We're going to talk about when we talk about individual classes of molecules. So intermolecular forces are darn important. London dispersion, dipole-dipole, and hydrogen bonds. But understanding what they are is a lot more beneficial to understanding where they overlap. Because something like this molecule, once we're getting bigger molecules as we get deeper into organic chemistry, and they can have multiple intermolecular forces that apply to one molecule. All right, mostly review. I would actually hit those questions in your textbook, in the chapter and into the chapter. Make sure you understand this stuff really, really well. The better you do on this early stuff in organic, it's going to translate into better performance in later chapters as well.